Welcome to Mathematics for Machine Learning. Today we will look at a number of standard unconstrained optimization algorithms. So algorithms that aim to minimize an arbitrary function that inputs a vector. So the problem statement of unconstrained minimization is that we have some function f, which would be typically going from Rn, or basically some domain of f, if you want to keep it more general, to R. One dimensions, it might, for example, look like this, where on the one dimension we have our x, and then the other one we have our f of x. And the goal is to find a minimum. For example, here's a local minimum, or ideally we would find this global minimum. We assume that f is twice continuously differentiable for the algorithms that we look at. And we are looking for p star, which is this optimum. So we would call this here p star. It's the infimum of x, and we hope that it is attained and finite. Unconstrained optimization methods produce a sequence of points, so they're iterative, produce a points xk from the domain of f, right? Typically from R to the power of n, for the iterations 0, 1, and so on. And this sequence hopefully would go towards p star. Alternatively, you could view iterative methods for unconstrained minimization also as iterative methods for solving the optimality condition, namely that the gradient of f at x star should be 0. So you could either say, okay, we're generating a series of points that go towards p star, or we are basically iteratively setting the gradient to 0. They all start with an initial point that is called x0, could be randomly chosen, could be chosen in any other way. And from this initial point, then they would iterate by setting the point x at the iteration k plus 1 to our current estimate xk, plus t of k, where t is the step size or step length at iteration k, times delta xk, where delta x is a step direction or search direction. And the goal is that in each iteration the function value at x k plus 1, so our next estimate, should be smaller than the function value at our current estimate for the inputs x. Typically, the direction, the step direction or search direction, is chosen such that the product of the gradient and the search direction is smaller than 0, which means that the search direction is a so-called descent direction. So if the inner product between the search direction and the gradient is negative, then you're going into a direction that decreases your function value. You can visualize this. For example, we have a function in R2. Here we have our x star, or minimum. Here we have our current xk. If we compute the gradient would look into this direction here. So this would be the gradient of f, where these are the level sets of f. Then any point, any direction that goes on this side here, that we could choose as our delta xk, would produce a negative inner product with the gradient, and thus be a descent direction. Whereas if we chose a vector that had, that went in this direction here, it would form a positive inner product with the gradient and would be an ascent direction. Or if we chose something on this line, then the gradient and the direction would actually be orthogonal to each other, and we would not be guaranteed to have a descent direction. So a descent direction for smooth functions that are twice continuously differentiable always guarantee a descent direction if the inner product with the gradient is negative. So any general descent method would utilize such a delta x that is a descent direction. So it's given a starting point x from the domain of the function, we would determine some descent direction, delta x, perform a line search along this descent direction, and the line search, we will get to know, is a way to choose a step size. So it's something that we can multiply with our current descent direction. So the step size basically tells you how far we would go along this line. So if this is our descent direction, if you choose a step size that is larger than 1, you would go over here. If you choose a step size that is smaller than 1, you would go here. And you can see that if we choose our step size too large, we would actually also not be guaranteed to decrease the function value, but at some point we might overshoot and increase it. So whereas if we choose the step size too small, then we would make very small steps. But once we have found a good step size, we would perform an update. So we would set the value for x to the current value of x plus the step size times the descent direction. And we would iterate until some stopping criterion is satisfied. For example, we could look at the norm of the gradient at our new point x. So once the gradient is close to 0, it should have a small norm and we can stop. As we said, during line search, we have to find a good t, a good step size for our iteration. Once you have a function, again, let's draw some f. These are again the level sets. Here we have our minimum, x star. Here we have our current x. Once you have found a search direction, for example, your search direction might be this one here, which would be roughly the negative gradient. Your line search is called a line search because it's a one-dimensional optimization problem. You're basically limiting yourself to this line here. You can only go in this direction. And if you then display, basically you're cutting the graph of your function along this descent direction, you are ending up with a one-dimensional optimization problem such as this. And so basically starting here, this would be our current point x. So if we set t equals 0, which means that we don't perform an update, we would just stay here. And ideally, you would like to minimize this one-dimensional search problem. So the minimum would be somewhere here. That would be the result of minimizing exactly this line search. So this one-dimensional function that we get along this line. So you can imagine cutting here, and basically before you had a bowl, you're cutting the bowl, you only see the contour of the bowl. Some line search types would actually perform an exact minimization of this one-dimensional function. So sometimes that is a good thing to do and cheap to do. You can do that using a simple one-dimensional optimization algorithm. Maybe you could even do it analytically by setting the derivative of this one-dimensional function to 0. Most of the time, however, an exact line search is more costly than doing an approximate line search and instead doing more steps. So that might actually help you bring you quicker to your real optimum of the function. And one approximate line search is the so-called backtracking line search, where you introduce two parameters, alpha between 0 and 1/2 and beta between 0 and 1. And what you would do is you would start with t equals 1 and repeat to multiply t with beta. So you would, each multiplication would reduce the step size because b is smaller than 1. Typically, it could be something like 1/2. You could always halve the step size, or it could be 0.9, which means that you would reduce it only slightly. And you would do that as long as the following condition is not yet met, or until it is met, until f of x plus t times delta x, so a new function value, is smaller than a linear function starting at our current estimate. So remember that using the first order Taylor expansion, we can find a linear function that has the same derivative as this one-dimensional function here at our current point x. And this linear function would be f of x plus delta f of x times the descent direction times t. If you discount this by alpha, where alpha would be a number between 0 and 1/2, you're basically saying, well, you still get a linear function, but it's a linear function. It doesn't have the same derivative at our current point x. But it's a linear function that is, that goes down less steep, for example, 1/2 less steep than our first order Taylor expansion. And the assumption is that somehow between these two lies the actual graph and the actual minimum. So you somehow want to be below this graph in your function estimate. So you pick a t, you evaluate f with your current descent given that new t, and you look whether it is under this line here. Here you would have overshot, you would backtrack, again overshot, you would backtrack again, and hopefully be somewhere here in this region. Once you're below here, you would stop. So you're not guaranteed to have the global optimum, or not the global optimum, but the optimum of this one-dimensional line search function, but be, somewhere in this part of the function where we can guarantee that the function value is smaller than our current function value. So all of this is below our current function value, right? As we said, there's a trade-off between an expensive line search that is exact or gives you a better minimization of this linearized function, and a cheaper line search that doesn't give you the best step size, but allows you to do more iterates. And the other extreme to doing an exact line search would be to not do any line search at all. In, for example, stochastic gradient descent, the computing a gradient is cheap enough that you wouldn't want to do a line search in practice, and thus often just set t, the step size, to a very small constant, for example 10 to the minus 3, 10 to the minus 4, and as you iterate, you would decrease t over the next iterations. So you would do a step with 10 to the minus 3, and compute a new gradient, and in the next iteration you may actually slightly decrease your step size, and so on, until you hopefully arrive at an optimum. If this constant is too large, you're more likely to overshoot. And if this constant is too small, your individual steps will be too small and you will have to do a lot of iterates. So there is again a trade-off in how you choose this initial step size and your schedule for decreasing the step sizes. And several different strategies have been proposed in the deep learning community. The most common version of the descent algorithm would be gradient descent. So it's a general descent method where you choose the step direction as the negative gradient. We said that any vector that has a negative inner product with the gradient would be a descent direction. And obviously the negative gradient has a negative inner product with the positive gradient. So it is a descent direction. In fact, as long as you're measuring your error with the L2 norm, it would be the steepest descent direction. So it would be the direction where the function decreases the fastest at our current point x. Given a starting point x, the gradient descent method would iterate as follows. You set your search direction to the negative gradient. You perform a line search, could be any of the methods discussed, exact line search, backtracking line search, or maybe no line search at all, could also be a different method. And then you update. You set your next iterate to our current iterate plus your step size that you have determined via line search times your negative gradient. And you do so until stopping criterion has been reached. And typically it would be in the form of the L2 norm of your gradient. And as that is small enough, so smaller or equal to some small value epsilon, then you would stop and say my gradient is close enough to 0, which means I have reached a minimum of my function. It's a very simple method. However, as we will see, it's often too slow. Let's look, for example, at a quadratic problem in R square. So a function would be 1/2 times the first coordinate x1 squared plus positive value gamma times our second coordinate squared. We even do an exact line search starting at point x0 equal to gamma 1. In the following graph, you see this function for gamma equals 10. So we start out with x0 here at 10, 1 and iterate. So if you compute the gradient would be orthogonal to our current level set here at this point, so it would point in this direction. So our negative gradient, our step direction goes in the opposite direction, and we perform an exact line search. So this is the minimum of this one-dimensional function here, and that would be our x1, and there we would again compute our gradient, which in this case would look in this direction, and we would do an exact line search in this direction, opposite of the gradient, and so on and so forth. We see that in general the iterates here for this function would be gamma times the fraction gamma times gamma minus 1 divided by gamma plus 1 to the power of k for x1, and for x2, our second coordinate, it would be minus gamma minus 1 divided by gamma plus 1 to the power of k. And we see that this method would be very slow for very large gamma or for gamma that are much smaller than 1, that are close to 0. So for a gamma equals to 1, the level sets of this function would just be circles. In this case, gradient descent would be very fast in convergence because you directly land at the optimum. But for a gamma that is very small or very large, so very close to 0 or a very large positive number, you get these skewed ellipses. And there you see that, as in the example, the iterate would jump around and fluctuate a lot. Let's look at the second example, in this case a non-quadratic function. It would again be a function element R2. The function is given by e to the power of the sum of x1 plus 3x2 minus 0.1 plus e to the power of x1 minus 3x2 minus 0.1 plus the e to the power of minus x1 minus 0.1. Here you again see the level sets of a function with a minimum here. And we start out with some initial point x0. If you run here with a backtracking line search, we see that we are again fluctuating quite a bit around. However, if we do an exact line search, in this case, we're actually very fast in convergence. So as we have seen in these examples, while gradient descent is an extremely simple method and easy to implement, depending on the line search that you're using, and especially on the contours of our level sets of our function, it can get very slow. Let's look at a third example in R to the 100. So in this case, we won't draw the function, but the function is given by a number of constants times our parameter vector, which is a vector from R100, minus the sum from I equals 1 to 500 of log of bi minus ai transpose x. In this case, if we compare the distance between our minimum p star to our current estimate as a function of our current iteration, so we're starting with an iteration of 0, and then as we iterate, the distance between our current estimate and the optimum obviously gets smaller. The distance is plotted here on a log scale. So this is a so-called semi-log plot. And the iteration is plotted in a linear scale. Then we see that there is no big difference between an exact line search and a backtracking line search for this particular problem. And because this is close to a straight line on this semi-log plot, we would actually call this a linear convergence of our algorithm. So I've already stated that gradient descent corresponds to steepest descent as long as we're measuring our error with an L2 norm, so a Euclidean norm. Generally, if we have some arbitrary norm, the normalized steepest descent direction would be the following. So we have our current point x and we have a norm, then the descent direction delta x normalized steepest descent would be the argmin of the product of the gradient and some vector v, where v has a norm in our current norm equals 1. So we are minimizing here over v. Of course, if the norm would be our Euclidean norm, then our argmin would be the negative gradient divided by the norm of the negative gradient. So it would be a unit norm vector that points in the opposite direction of the gradient. But for other norms, this descent direction may look different. We can interpret this as follows, that for a small v, so a v that has a small norm, using the first order Taylor expansion, our function value at our current estimate x plus v can be approximated by the linearized function f of x plus the product of our gradient times v. So the search direction here is always a unit norm step with the most negative directional derivative. Of course, you can then still do a line search along this direction. In principle, you can also perform unnormalized steepest descent, in which case you would use your normalized steepest descent search direction and multiply it by the norm of the gradient. And obviously, this then satisfies that the gradient times our steepest descent direction would be equal to the negative squared norm of our gradient. Steepest descent is a general descent method where our descent direction is given by our delta steepest descent, and it has convergence properties similar to gradient descent, which, as we said, is an instance of steepest descent when we're measuring the norm with the Euclidean norm. So let's look at other examples. We already said that for the Euclidean norm, delta xsd would be the negative gradient, so that would be our gradient descent direction. But in principle, we could have any other type of norm. For example, we could have a quadratic norm defined by a symmetric and positive definite matrix A that is given by the squared form of our vector x with A to the power of 1/2, so the square root of this squared form in A. In this case, the steepest descent direction would be given by minus the inverse of the matrix A times our gradient. So generally, if we look at these quadratic norms for some arbitrary matrix A, the level set of those norms correspond to ellipses. And if we, for example, look at our function currently here, we compute the negative gradient, then the non-normalized steepest descent direction for this particular norm would point in this direction here. So it would not align anymore with the gradient. An alternative norm to use would be the L1 norm, which is given by the sum of the absolute values of a particular vector that we're taking the norm of. Here we see the L1 norm. In this case, for the L1 norm, the level sets are these diamond shapes. And we again see that the steepest descent direction does not align with the negative gradient, but rather follows only a single coordinate. So if this is R2, we're only moving along one of the two dimensions. In fact, the search direction for the L1 norm is given by minus the partial derivative of f with respect to 1xi times that particular standard basis vector ei, and it would be done for that dimension where the absolute value of the partial derivative is equal to the infinite norm of the gradient. Remember, the infinite norm is given by the maximum absolute value of the vector. So we would look at all the values of the gradient and choose the coordinate that has the largest absolute value in the gradient. The choice of the norm is important for the speed of convergence of steepest descent. Here we look at the same example in R2 as before, but for two different norms. So here we see the unit balls of the corresponding quadratic norms. And we see that if we choose this norm here, we get a quick convergence, and if we choose this other norm here, we get a slow convergence. In both cases, we have performed backtracking line search, and the ellipses show the unit balls of the particular norm. So for these quadratic norms, you can also interpret the steepest descent with this particular quadratic norm to perform gradient descent after a change of variables, where you take your positive definite matrix P, build the square root of P, as we have learned, for example, using the singular value decomposition, and multiplying this square root with x. And then you're doing gradient descent on the resulting new coordinate x tilde. The last method that I would like to discuss is Newton's method. In Newton's method, the descent direction is chosen as follows. So the Newton direction is given by minus the Hessian of f at our current point x inverse times the gradient of f at our point x. There are two different ways to interpret Newton's method. One would be to look at it as performing a minimization of the second order Taylor expansion of our current function. So you're approximating f by a second order Taylor expansion. So f of x plus v becomes approximated by f of x plus the gradient times our displacement vector v plus 1/2 times the squared form of v in the Hessian matrix. Now you have replaced f by f hat, and you do, instead of minimizing f, which is not easily possible, you're now performing minimization of the Taylor expansion. So we can prove that this indeed minimizes the second order Taylor expansion. So what we're looking for is an optimal v that minimizes f hat. So what we need to compute is the gradient of f hat with respect to v. That is given by, well, here there is no v, so this goes away. Here there is a v, so we are ending up with the gradient of f plus, here we have a squared form, so the 1/2 goes away, and we're left with the Hessian of f of x times v. Now we set this to 0, which means now we bring the gradient to the right side by subtracting the gradient, and thus the Hessian of f of x v equals to minus the gradient of f x. And in order to solve now for v, we have to get rid of the Hessian here, which means that we have to multiply both sides with the inverse of the Hessian, assuming that the Hessian is invertible, of course. And we see that the result of this is exactly equal to our delta x n t. An alternative interpretation is that we are solving the linearized optimality condition, where we are linearizing our gradient. So we're basically computing our gradient and approximating it with, well, basically the gradient of our second order Taylor expansion, which is equal to the gradient of f plus the Hessian of f times v. And then we solve for this optimality condition by setting this gradient to 0, which is again exactly the computation that we have done here. So if this is the gradient at our current point, then we are basically looking for a 0 in this approximated gradient. An interpretation of the Newton step could be that the Newton step is steepest descent if you have a local Hessian norm. So instead of having a fixed matrix A, you always build the norm based on your current local Hessian by performing this squared form and taking the square root of the squared form. So this would be the norm in the Hessian of f. So here basically you have the norm not being based on a fixed matrix, but on a matrix that can vary, that itself is a function, so to say. And we can again look at this in our example. So we have our current estimate x, and we compute the Hessian, and this would be the unit ball of this Hessian norm. So this would be the set of all points that make the square root of the squared form, or the squared form itself, equal to 1. As denoted here. And the arrow would again show the negative gradient. And you can see that the furthest we can actually go on this ellipse would be here. So you can see that the Newton step gets much closer to the optimum than steepest descent would. One important quantity that I would like to introduce around Newton's method is the Newton decrement, lambda x. It's defined as the square root of the squared form in the Hessian of the gradient vector. And it is a measure of proximity between our current point x, where you're estimating this lambda, to our optimum x star. In fact, it estimates this proximity between f of x and our function value at the optimum using the quadratic Taylor expansion of f. So it estimates the location of x star as the minimum of this Taylor expansion. It's f of x minus the infimum of this Taylor expansion of f. And this equals to 1/2 lambda squared. It also is equal to the norm of the Newton step in the Hessian norm. So lambda x squared equals to the squared form in the Hessian of our Newton step. So remember, delta x and t equals to minus the Hessian of f at x inverse times the gradient of f at x. And the third interpretation of the Newton decrement is that it is the directional derivative in the Newton direction. So the inner product of the gradient and our Newton direction is equals to the negative Newton decrement squared. So let's summarize the complete Newton's method. So we're starting with a point from the domain of the function. We have a tolerance epsilon, that is a small number larger than 0 as a parameter. And now we repeat, we compute the Newton step and the Newton decrement. And the search direction becomes to minus the inverse of the Hessian times the gradient. And our Newton decrement lambda squared is equals to the squared form of the gradient, the inverse Hessian times the gradient. We have our stopping criterion. We would stop if the Newton decrement is small enough. So remember that the Newton decrement is a measure of proximity between our current point and x star as approximated or estimated by our second order Taylor expansion. And then we perform a line search. We choose a step size t by backtracking line search. And then we perform an update by setting our new iterate to our current iterate plus t times our search direction. In principle, if you are really sure that the Hessian is always positive definite and so on, and your function is nicely well behaved, then often one doesn't even perform a line search. You could just iterate by always minimizing your second order Taylor expansion and then at this minimum do the next Taylor expansion. So some people implement Newton's method without a line search, depending on the problem. A nice property of Newton's method is that it is invariant to affine transformation. That means if you perform a linear change of coordinates, you would still get the same or equivalent, better said, steps. So if you have a linear map T, then the iterates for f tilde of y equals to the f of t times y with a starting point y0, where y0 is equals to x0 multiplied by the inverse of our linear map, r yk, which equals to, again, t inverse to xk. So it doesn't matter whether we apply this linear map or not. We could either iterate in y or in x, and we would get exactly the same number of iterations and so on and so forth. Remember that in Newton's method, we compute x and t as minus the Hessian of f at x inverse times the gradient of f. So we need to invert the Hessian matrix. So Newton methods requires an invertible Hessian matrix. In fact, if the Hessian matrix is not positive definite, this Newton direction may not even be defined. And even when it is defined, if the Hessian has a negative eigenvalue, so if it is indefinite, then x and t may not be a search direction. So because it may happen that the inner product of the gradient and our Newton update is smaller than 0, which means that we don't have a descent direction. In that case, we can still run Newton's method, but we have to be careful, and typically we would use some adjusted line search methods to modify the search direction. So if the line search realizes that the function doesn't even decrease because we are actually going along an ascent direction, then there needs to be a fallback for our search direction. So it doesn't only need to adjust the step size, but also the search direction. And with the introduction of Newton's method, I would like to conclude for today. Remember, we have looked at various optimization methods for non-constrained problems where we're looking to iterate over a vector x in order to find the minimum of a function. We introduced general descent methods, most prominently the gradient descent method and various other steepest descent methods for different norms. And we have introduced the so-called second order method in Newton's method, which can be interpreted as a steepest descent method in a Hessian norm. And with this, I want to say goodbye. See you next time.